physical properties of the haloalkanes. And that first one is density. So in this density, both alkyl fluorides and alkyl chlorides are less dense than water, but both alkyl bromides and alkyl iodides are more denser than water. So I will write down here how the density varies. Alkyl iodide is more denser than the alkyl bromide, which is more than the water, and which is more than the alkyl chloride, and last one is alkyl fluorides. So when the number of halogens increases, density also increases. So I will take here, for example, within the same molecule, if you take CCl4, density is more than the CHCl3, whose density is more than the CH2Cl2, whose density is more than the water, but water density is more than the monohalogen compounds. Here we have taken the only monohalogen compounds. So both the chlorides and fluorides means monochlorides density is less than the water. Now let's take the boiling point. So boiling point of the compound generally depends on the size of the atom. Boiling point depends on the size of halogen atom here in alkyl halides. So what happens here when the size of the alkyl halide increases? When the size increases, automatically van der Waals forces also increase and automatically boiling point also increases. So among these iodide, bromide, chloride and fluoride, iodide size is more. So that's why if you take CH3I, whose boiling point is more than its respective CH3Br, more than CH3Cl and more than CH3F fluorides. But when the number of halogen atoms increase, then also the boiling point increase within the same molecule. For example, if you take the chlorides, CCl4 boiling point is more than the CHCl3 chloroform, whose boiling point is more than the CH2Cl2, which is more than the CH3Cl. So when the number of chlorine atoms increases, means halogen atoms increases, and automatically boiling point value also increases. Now let us see the dipole moment. So in this dipole moment, we know that dipole moment value mu is equals to Q into D. Q is the quantity of the charge, D is the distance between the two nuclei of the bonded atoms. So dipole moment depend on the both of this charge as well as the distance also. If distance increase, dipole moment value also increase. At the same time, the charge also must and should increase. So if you take the fluorides, chlorides, bromides and iodides, we know that on moving down the group, size increase, but electronegativity charge present on that halides also decreases, only size increase. So when you see the dipole moment of different halogen compounds, chlorides dipole moment value is more than the fluorides, which is more than the bromides, which is more than the iodides. But generally people expect that fluoride should have the higher dipole moment than the fluorine, because the fluorine electronegativity is more and it will drag the more charge over it. But at the same time, the size is very less, fluorine. See, if you take the carbon atom and the fluorine atom, since the size of the fluorine atom is less, so the bond length decreases or distance decreases. But for the same carbon, if you take the chlorine size is bigger. So sufficient size is there, so that chlorine may have the less charge, but the charge is predominated over by the distance. That's why dipole moment value of the monofluorides is more than the fluorides, which is more than the bromides and respectively than the iodides. Let us see chemical properties of halides. So in this lesson I am discussing only haloalkanes, not the haloarenes. Haloarenes separately we shall discuss in the aromatic compounds. So we know that chemical properties. In this particular case, if you see a particular normal alkyl halide like this. So in this normal alkyl halide, halogen is more electronegative than the carbon, so that it withdraws this pair of electrons more towards its side. As a result, this halogen gets the partial negative charge, carbon gets the partial positive charge. So when carbon gets the partial positive charge, then nucleophiles can easily approach this particular carbon to attack, so that they can replace this halogen in the form of the halide ion. So we get the RCH2 nucleophile plus X minus. X minus is also nucleophile. So how to understand, because both are the negative charged particles only, then you may think that again X minus may attack over here to replace this nucleophile. So here I shall explain a small concept, that the one that is leaving, this is the leaving group. So whatever the anion is leaving is called as the leaving group. Then in which cases this becomes a better leaving group. Better leaving group means a weaker base is always a better leaving group, because after the removal of the negative anion, if it is stabilized on its own, means if the anion is able to stabilize its negative charge, then it will not donate the pair of electrons. Then obviously it is called as the weaker base. So weaker bases are always stable and they are the better leaving groups. So I will write down the point here. A weaker base is always a better leaving group. Now I shall take some examples. Later we will come to this particular point. So the examples are, you just take the first example, ammonia and water. Okay, so between these two, which is the strong base? Strong base is a strong base always acts as the nucleophile. Weak base always acts as the leaving group. Okay, so we know that ammonia is a strong base. So strong base is the nucleophile, always acts as a nucleophile, and weak base is the better leaving group. So here H2O is the leaving group. I'll take one more example. Second one is, you take in a particular molecule NH3 and NH2 minus, both are there. Between these two, which is the strong nucleophile, which is the better leaving group? So NH2 minus is the better strong base. Why? Because negative charge is present. Here lone pair of electrons are present, but negative charge predominates over that. So here this is the strong base. Strong base means it acts as the nucleophile. And weak base is always the leaving group. Now let us take the third compound, OH minus and HS minus. So if when it comes to this particular type, then which is the better leaving group, which is the strong nucleophile? Then I have to explain certain concept here. So both of these compounds, if you take their respective compounds H2O and H2S. So H2O after the loss of H plus ion gives OH minus. H2S after the loss of H plus ion giving HS minus. Between these two compounds, on moving down the group, we know that in the 16th and 17th group elements, hydrides, acidity increases. Why? Because distance between the central atom 16th group element and the hydrogen increases. So the lasting nature of the H plus ion increases, so that their acidity increases. Means between H2O and H2S, H2 is the strong acid, H2S is the strong acid. So stronger acid means this must be the weak base. This is the weak acid, so this is the strong base. Okay. So this is the strong acid. So this is the weak base. And here this is the weak acid. So this is the strong base. So weak base is which one? HS minus. So HS minus is the weak base, hence it is the better leaving group. And OH minus is not the better leaving group. So when OH minus, HS minus both are there, OH minus acts as the nucleophile. I am just discussing the common nucleophiles and leaving groups, what we are generally what we encounter in the regular classes. Then they may ask the question about the, see, there may be F minus, Cl minus, Br minus and I minus. If these are there, then how to decide which is the better leaving group, which is the that means nucleophile, better nucleophile. So I shall take these examples. You just take HF molecule, HCl molecule. Always you take their respect to hydrides, because hydrides gives the acidic nature. So once a weak acid means stronger base, like that we can easily expect. HF, HCl, HBr, HI. So on moving down the group, in the hydrides of the both the 16th as well as the 17th groups, acidic nature increases. Acidity increases. So when acidity increases, means this HF, HCl, HBr, HI, after the loss of their respective H plus ions, they form the respective halides. HF forms fluoride, HCl forms chloride, HBr forms bromide, HI forms iodide. So among these, we said that acidic nature increases. So when acidic nature increases, then this is a strong acid. This becomes the strong acid. So this becomes the weak base. Means on moving down the group, basic nature, when acidic nature increases, basicity decreases. When basicity decreases, leaving nature increases. So that among all these, I minus is the better leaving group. So that we can write like this, leaving ability. So in this way, just you take the respective hydrides always, then you can easily understand which is the strong base, which is the weak base, which is the strong nucleophile, which is the better leaving group. So when it comes to the, generally they ask the question in the examinations like this: alcohol and H2O. So they may ask between these two compounds, which is the strong nucleophile, which is the weak nucleophile or which is the better leaving group. So for this we should understand their acidic nature first of all. So here CH3OH, methyl alcohol on loss of H plus ion, it forms its respect to methoxide ion. Similarly, H2O on loss of H plus ion, it forms its respect to OH minus ion. So in these two compounds, here methyl group is the plus I group, which still relays electrons to the oxygen, makes the methoxide ion less stable. So less stable means this is the unstable one. Okay. So here no such groups are there to release. So OH minus is the more stable. More stable means this is the more stable means it can easily exist, so that it is a weak base. So CH3OH can release the H plus ion and forms its respect to methoxide ion. H2O releases H plus ion, can form the OH minus ion. 1 minute. Yeah. If we discuss here, methyl group is releasing the electrons to the oxygen so that it becomes more negative, and methoxide ion is unstable. OH minus ion is stable. So stable one is always, as we discussed here, starting part. If any negative ion is more stable, so stable one is always the weaker base, and it can easily be stabilized and it leaves the particular group. So that here OH minus ion is the more stable compared to this one. So more stable means it is not ready to release its negative, means electrons. But methoxide ion is unstable, so that it is ready to lose its particular lone pair of electrons. So this is a strong base. This is the strong base, and here it is not ready to lose the electrons to the positive charged one. So in comparison to this one, so this is the weak base. So when you compare these two, this is the better leaving group. OH minus ion is the better leaving group, and this is, since unstable, immediately abstract the H plus ion and come back to its respective position. So better leaving group is this one, and when you compare their acidic nature, this is the strong acid, because after the loss of H plus ion, its negative charge is stabilized, and here it is a weak acid, because after the loss of H plus ion, it cannot be stabilized because of the positive plus I effect. So that when alcohol and water is taken, water is the strong acid compared to the alcohol. At the same time, the respective anions, if you take, the respective anion means OH minus ion is a better leaving group in comparison to the alkoxide ion. Since alkoxide ion is not the leaving group, then what it will be? It will be the strong nucleophile. When it is a strong nucleophile, then what about the OH minus ion? It is a weak nucleophile. Means it cannot generally attack. So in this way, you can compare the nucleophilicity and the basicity. Now come to the first point. So now here, a nucleophile is initiating the reaction and replaces the another nucleophile. So we say that these alkyl halides are participating in the nucleophilic substitution reactions. So these nucleophilic substitution reactions are of actually 4 types are there, but in your NEET syllabus only 2 types are there, that we shall discuss. So types of nucleophilic substitution reactions. Okay, so in this type of nucleophilic substitution reaction, these are of two types. They are SN2 reactions, second one is SN1 reactions, third one is SNI reactions, and the fourth one is NGP, neighboring group participation, but we shall discuss these two. And these two, if you want, I will post separate videos, but discussion wise these are very important for us. So what does it mean by SN2 reaction? So anyhow, I will take the reaction separately, so there we shall discuss separately again. SN2 reaction. So in this SN2 reaction, this 2 stands for the bi, means 2 molecules, bimolecular. N stands for the nucleophilic, means we go in the reverse way, 2NS like this, and S stands for the substitution. So these are called the bimolecular nucleophilic substitution reactions. So what does it mean by bimolecular? Bimolecular in this sense, 2 molecules are participating in the rate determining step, RDS. We know that what does it mean by rate determining step? The slowest step in the mechanism is called the rate determining step. So 2 molecules are participating in the rate determining step, and this gives one more information that bimolecular reaction, since 2 is there, we can easily say that order of the reaction is 2. Order of the reaction is 2. That means these SN2 reactions are second order reactions. Second order reactions. Then what type of alkyl halides preferentially participate in this SN2 reaction? Generally, methyl halides preferably participate in the SN2 reaction. Later, primary alkyl halides. Next one, secondary alkyl halides. Next one, tertiary alkyl halides. But secondary and tertiary generally do not participate in the SN2 reaction. Only these two preferentially participate in the SN2 reaction. So we shall take some example. So directly I'll take the one chiral molecule. Okay, I'll take the CH3X only, hydrogen, here one hydrogen is there, here some halogen, means you can take the chlorine or bromine. So here one hydrogen is present. Okay. So when it is subjected with the aqueous KOH, here OH minus is there. OH minus is the strong nucleophile, and this OH minus approaches this particular carbon from the backside. The reason is, here we know that carbon gets the partial positive charge, the halogen gets the partial negative charge. Okay, and this is negative charge, this is the negative charge, they repel each other. So that is the reason why this particular OH minus and approaches the halogen bearing carbon atom from the backside of the halogen bearing carbon atom, and finally gives, so here bromine starts leaving the carbon, it starts breaking the carbon halogen bond, and OH minus start developing the carbon hydrogen bond. Here hydrogen is there, and here one hydrogen, and here one hydrogen. This is called the transition state. Okay, so this transition state is very unstable because carbon able to form only 4 bonds, not the 5 bonds. So simultaneously approaching and disconnecting takes place, so that finally Br minus will leave the carbon molecule and we get this particular alcohol molecule. And if you observe this particular molecule, the OH minus ion position is exactly opposite to the position of the leaving group. So we get the inverted configuration product. Okay, I'll write down that one. In SN2 reaction, the new nucleophile is placed exactly opposite to the position of the leaving group. Position of the leaving group. So automatically when we are getting the inverted configuration, so the configuration of the product is inverted configuration and this process is called Walden inversion. Okay, you can take any other molecules also just to understand the SN2 reaction. So in this particular one, I need to discuss one more important thing, that is the attacking of the nucleophile over the alkyl halide is a slow step. So it is called the rate determining step, slow step. So in this slow step, how many reactant molecules are involved? One is alkyl halide, second one is the nucleophile. Means the rate of the reaction, speed of this reaction depends on both of these. So here we can write rate of this reaction. Rate is directly proportional to the concentration of alkyl halide and the concentration of the nucleophile. How many nucleophiles are involved? Only one. How many alkyl halides are involved? Only one. So 1 plus 1 order is equals to 1 plus 1, that equals to 2. Since order of this reaction is 2 and since only 2 molecules are participating in the rate determining step, it is called the SN2 reaction. Okay, and let us take one more example. Later we shall go for the next example. You see here, hydrogen, here CH3, and here also hydrogen is present. To this you just subject the KCN, okay, K plus and Cn minus, carbon carries negative charge in case of the potassium. If it is silver cyanide means nitrogen carries the charge. So now here this is the secondary alkyl halide. So secondary alkyl halides usually participate in the SN1 reaction only, so that this negative charge will attack from the opposite side of the halogen, so that halide will be removed. So Cn position will be the position of the hydrogen and hydrogen will be pushed to the upper. So finally it becomes like this. CH3, hydrogen, hydrogen, and it is cyanide. Now let's take one more example. HCl, CH3, CH2, CH3, NaSH. So Na plus SH minus. So this SH minus again approaches from the opposite side of the chlorine. So that SH position will be the position of the hydrogen position will come over here. So we get the molecule like this: CH3, C2H5, SH, hydrogen. Next, hydrogen, OTS, phenyl group, CH3. OTS means tosyl group. These leaving groups I will make one more video. There you will get the clearer picture about the leaving groups, because that is not necessary for the NEET program. That's why I am not discussing the leaving groups, but separate video I will make. There you get the complete idea. So this OH acetate ion will attack from the opposite side of the tosylate ion, and we get the molecule like this: pH and CH3. And here I am writing the inverted image so that here it looks like this: O, C double bond O, CH3, and you take the hydrogen, and if you put one mirror over here, then or below of that one, you will get its mirror image. Okay, and the last one is this is alkyl halide, just subject with the aqueous KOH. Here no stereochemistry is mentioned. In such cases you don't need to do anything, just replace this bromine with OH. So you will get the molecule. And what other SN2 reactions are? So other SN2 reactions I am going to write down. So as I am going to discuss in a single place, so this video may not be the more lengthy video, otherwise it may take the 2 or 3 videos to make this one, 2 to 3 classes. So here we shall take the alkyl halide. So this alkyl halide reactions, different reactions, let us discuss. So what happens if aqueous KOH is, these are all SN2 reactions only. So separately you don't read, because generally in a classroom or in the notebook what we teach, reaction with aqueous KOH, reaction with sodium alkoxide, like this we used to teach, but that is not necessary. So once all SN2 reactions you are going to learn here only. So aqueous KOH means replace this alcohol halogen and gives the alcohol. Next, subject with the R-O minus Na plus. What is the name of this reaction? The name of this reaction is alkyl halide with sodium alkoxide. It is called the Williamson synthesis. Ethers, Williamson's ether synthesis. So Williamson's ether synthesis is the part of the, it is type of the SN2 reaction. So you shall get the, here we shall take the R dash, O, R dash. Next one is R dash S Na, means instead of the oxygen you are taking the sulfur. So here you will get the R S R dash, thioether. Next we shall take the NaSH, or you can take the KSH, like KOH we have taken, so in the place of the oxygen you just take the sulfur. So it is Na plus S minus H, K plus S minus H, so that you shall get the RSH. And next you just take the NaN2, NaN3, sodazide. So Na plus N3 minus, we get the R, N double bond, N double bond, N, this is positive charged one, this is the negative charged one. So here if you take NaCN or KCN, potassium cyanide, so here we get the RCN molecule, means carbon will be connected. So let us take the this side also. So what happens if sodium alkynides we have discussed, minus Na plus. Remember that this is the primary or secondary alkyl halide. You should remember that. So I will write down here primary or secondary, not the tertiary. Tertiary means these are all will follow again the this reaction, SN1 reaction. The same reagents but give the same products but with different mechanism, SN1 mechanism. So here we shall get this is R dash I'll take. So it will be replaced with the C triple bond C R dash. Next one is R C double bond O minus. So here we get the R O C double bond O R dash. So R dash must be to the C double bond O carbon. And next NaNO2. Na plus NO2 minus. So in this NO2 minus the structure is O single bond N double bond O. See, this oxygen carries negative charge. So this negative charge attacks over here. So that bond happens between the carbon and nitrogen through oxygen. So the bond will be like this. So this is called as the nitrite. And if you take the RMgX, Grignard reagent, so this will be the charge. R dash I'll take here. So this will attack over here and finally gives the alkyl halides, reacts with the Grignard reagent and gives the alkane. Next RLI. So here also alkyl group, means when alkyl group is with the metallic compound, so that carries the negative charge. Alkyl group carries the negative charge. So these all gives the again alkanes. You see here, this is the preparation of the alkanes indirectly. And here Gilman's reagent R2CuLi, lithium dialkyl cuprate. This is R dash. Again it carries the negative charge, so that it gives again alkane molecule. Then if you take the lithium aluminum hydride, so here actually H minus is the attacking reagent. H minus carries the negative charge. So that shall attack over the alkyl group and replaces the hydrogen. So it is indirectly lithium aluminum hydride reduces the alkyl halides to alkanes. Because the lithium and aluminum both are the metals. Metals cannot attack because they carry the positive charge. The only one that carries the negative charge is H minus. Then what happens if we take separately AgCN? So if you take the AgCN, in this particular molecule, I will write down its structure, AgC triple bond N. So now nitrogen attacks. Why? Because carbon is not free to attack, just like in this case. In the case of the potassium cyanide, what is there? Carbon carries negative charge, potassium carries positive charge. Here carbon carries negative charge, sodium carries positive charge. So there is no bond, only attraction force is there, so that a carbon can easily attack this one alkyl halide, so they can develop the new carbon-carbon bond. So this is an example for the formation of the new carbon-carbon bond. Okay. So here carbon is not free enough to attack, so that this, in the case of the alkyl cyanide, the lone pair of electrons present on the nitrogen attacks over the alkyl group. So finally gives the N triple bond C. So later this bond will be broken. So nitrogen is attacked with the connected to the alkyl group and triple bond likes that only. And next one is what happens if you take the AgNO2. So AgNO2 means here the structure of this AgNO2 is AgON double bond O structure. Now nitrogen attacks, not the oxygen. So here we get the molecule structure like this, NO2. This is nitroalkanes. Okay. So these are all SN2 reactions if you take the primary alkyl halide as the reactant molecule, and do not forget this one. So since all reactions are being discussed in the single place, separately no need to discuss all this again and again. So now let us discuss the SN2. So SN2 reaction is over. Now we shall discuss the SN1 reaction. What is the SN1 reaction? Later we shall discuss the exceptions also. SN1 reaction. So it's a name. Here 1 stands for the single molecule. So single means unimolecular nucleophilic substitution reactions. As just now I said, unimolecular means only one molecule. One molecule is participating in rate determining step. Since only one molecule is participating, rate of the reaction depends on only single molecule. So the order of the reaction is first order. That is this one represents that first order only. So which alkyl halides preferably participate in the reaction? Let us see. Tertiary alkyl halides participate in SN1 reaction. Okay. So I'll take one example here. You see here, this is the CH3, and I shall take the molecule like this, C2H5. Different groups I'll take. C3H7. Here Br is there. Now if you subject this one with aqueous KOH, so the product will be CH3, C2H5, C3H7. So the OH may come either here C2H5, C3H7. So the OH may come over here. Means two products can be formed. So there are possibility for the formation of the two products. Let us see how these products are going to be formed. So first of all, we need to see the mechanism. So this mechanism involves two steps. Step 1. This is the formation of the carbocation. So how this formation of the carbocation takes place means this tertiary alkyl halide we shall take here. So this bond will be broken, carbon halogen bond. So here we get the CH3, C2H5, and now we can write the with that dotted lines. So that I am not writing here. I'll tell you why I am not writing this dotted lines and all this. I'll write like this only: C2H5, C3H7. This is the positive charged one, and Br minus will be removed. And in this case, this is the carbocation is formed. So the breaking of the bond is a very slow step. So it is a reversible step also. Rate determining steps are generally reversible steps. So in this rate determining step, only one alkyl halide is participated. Means the entire speed of the reaction depends only on the alkyl halide. And moreover, the thing what I want to discuss here is this carbon is sp3 hybridized. Shape is tetrahedral. But now this particular carbocation is sp2 hybridized and shape is planar. So formation of the carbocation intermediate is the rate determining step. Since it is planar in shape, so all these alkyl groups will come over to the same plane. Okay, now step 2. Step 2 is always generally fast step. So it is attacking of the nucleophile. So let us take this nucleophile here. So the nucleophile what we used here is OH minus. So this nucleophile may approach from the front side or it may approach from the back side also. So the chances of approaching this nucleophile from the back side is nearly 50 to 70% chances are there, and approaching from the front side is from 30 to 50% chances are there. So usually people say that racemic mixture will be formed. Though racemic mixture is formed, but one will be the major content, that is inverted configuration product is generally major one, but that is not mentioned in our notebook, so that we have to follow as per their concept. So CH3, C2H5, C3H7, here OH group, this is the inverted configuration product, this is the major one, to be very frank. The reason is this reaction takes place with a very fast, this is a fast step. Fast step in the sense, the moment this OH carbocation is formed, immediately OH minus attacks, because OH minus, Br minus, carbocation, reactant and all will be in the same reaction mixture. So when this is going to be disconnected, OH minus N will be ready to attack this carbocation the moment it is formed, because OH minus N separately will not come from the another corner of the bottle. This just lies beside of this bromine and carbon and all these methyl groups. OH minus may be present anywhere over here. So the moment it gets disconnected, OH minus N immediate attacks from the other side, because the OH minus N present from this side may not be able to approach the carbon very fast, because Br minus still exists over in that particular place. So that's why the chances of approaching this carbocation from the back side is 50 to 70%, but a front side is less. So that inverted configuration product is generally the major product. So racemic mixture actually 100% racemic mixture cannot be formed. So this is the product. So this type of the things happens only when the carbocation is formed. So when you take the SN2 reaction, there is no carbocation. No carbocation is formed. Only transition state is there. You can see here. No carbocation is formed. Only transition state is there. So that you just change the position of these three groups, you will get the next product with inverted configuration, and no rearrangement takes place in this SN2 reaction. But in the case of the SN1 reaction, it is not like that. Why? Because SN1 reaction involves the formation of the carbocation. Once the carbocation is formed in any particular chemical reaction as the intermediate product, then automatically the reaction will go for the stable carbocation. So 1,2 hydride shifts, 1,2 methyl shift, this all will take place till stable carbocation is formed. Okay. So now let us see here in this rate determining step how many reactant molecules are involved. Rate determining step, rate of this reaction is directly proportional to the concentration of tertiary alkyl halide. So when the concentration of the tertiary alkyl halide is more, then the reaction fast of this reaction also will be more, and only one reactant is there, so that order of this reaction is equals to 1, hence it is called as the first order reaction. So let us see some of the examples. which you will understand from this example what I am going to discuss one exceptional case. So when you use some aqueous KOH, immediately two products, we have tried on always two products because tertiary alkyl halide this is. This is the one product and next one is its mirror image. So from here you shall get the carbon and OH here and methyl group here and phenyl group is here. So these are the products. Then which compounds generally, which primary alkyl halides generally do not follow the SN1 mechanism but SN2 mechanism but still follow the SN1 mechanism. Let us see some exceptional things. So if you take benzyl alkyl halides, I will take bromide directly, benzyl bromide. This is the primary alkyl halide. But it follows, if you add aqueous KOH, no doubt it give CH2OH. I am not writing the two products. Why? Because this is not the chiral carbon. That's only one compound I am writing. Okay. And what type of mechanism it follows? It follows SN1 mechanism. The reason is this benzyl alkyl halide is able to form the stable carbocation. Benzyl carbocation is more stable. Why do the primary alkyl halides participating in the SN2 reaction? The reason is the primary alkyl halides are not able to form the stable carbocations. That's why they go with the transition state. But if any primary alkyl halide is able to form the stable carbocation, always follows the SN1 mechanism. So benzyl carbocation is stable, is able to form the stable benzyl carbocation, hence it forms the it follows the SN1 mechanism. For example, apart from this, one more is there. Let us take that also. CH3. 1 minute. I shall take with the CH2 double bond CH2 Br. This is allyl bromide. This allyl bromide is also primary alkyl halide. But when you add aqueous KOH, no doubt it gives the product. But the mechanism of this reaction is we have tried on SN1 mechanism. Here also SN1 mechanism. Because this allyl alkyl halide is able to form the stable carbocation. CH2 double bond CH2 plus. After the loss of Br minus N, whatever the alkyl halide is formed, that alkyl halide is stabilized by the resonance. So this is the stable carbocation. So due to the formation of the stable carbocation, both of these benzyl alkyl halides and allyl alkyl halides follows the SN1 mechanism but not the SN2 mechanism. Let us see the small reactions. Other reactions, you know that Wurtz reaction and all these we had already discussed. So that's why they are not there. I am not discussing those reactions. Only two more reactions. Let us see Swarts reaction. So Swarts reaction means it is a preparation of the alkyl fluorides. General alkyl fluorides cannot be prepared by direct fluorination reaction. I will write down here. Alkyl fluorides cannot be prepared by direct fluorination on alkanes as it is too violent. Too violent in the sense highly exothermic reaction, so not possible to control this reaction. So that's the reason why separating fluorinating agents are required. Fluorinating agents means we use the AsF3, SbF3, AgF silver fluoride, or HgF2, etc. These are all fluorinating agents. So when you take the alkyl chlorides, for example, C2H5Cl, when it is subject with the AgF, then a halogen exchange reaction takes place, so that you will get the C2H5F plus AgCl. Similarly, if you want CH3, Cl, Cl and CH3, so here two halogens you want to remove. In such cases, you can take the 2AgF, or else you can take the HgF2, only one molecule of HgF2, so it can replace two chlorines at a time. If you want to use the SbF3, just I am explaining, you can watch this video whenever you want, because I will share with you. So SbF3 means 3 halogens are there, here only 2 chlorines are there, so we have to equalize them. So you take 3 into 2 equals to 6, then you put 2 here, 2 into 3 equals to 6, so then you will get the CH3 F CH3 plus 2SbCl3. So these are the fluorinating agents. They just exchange the chlorine or bromine with the fluorine. And let us take the Finkelstein reaction. So in Finkelstein reaction, we prepare the iodides. Even preparation of the iodides using the direct halogenation is not the preferable one. Why? Because the reaction is too slow. So in this case, we use the combination of NaI with the acetone CH3 C double bond O CH3. Na is soluble in the acetone, or else you can take the methyl alcohol also. So you just take the alkyl chloride subject with the NaI, sodium iodide, in the presence of the acetone. They exchange the halogen and we get the alkyl iodide plus NaCl. Then the question arises here is, can't we prepare the bromides by taking the here iodide or NaCl, NaBr? We cannot. The reason is both NaCl and NaBr are insoluble in methyl alcohol or acetone. Since they are insoluble, once they don't soluble, then how can they react with the alkyl halide that is available in the liquid? One is in the solid state, one is in the liquid state, means that particular reaction is generally not possible. So hence we don't use the NaCl and NaBr as the reagents in this Finkelstein reaction. We use only sodium iodide. Thank you, students. If you like my explanation, if you understand my explanation, like this video, share it to your friends, comment whatever you think about my explanation, and finally do not forget to subscribe this channel. Thank you all.